Hey guys, today we are looking at 7.5, which is going to talk about algebraically defined vectors and the dot product. So when we're talking about algebraically defined vectors, we are starting with the initial point of the vector at the origin of our coordinate grid, and then the end point of the vector is at the point A comma B. So that's this point up here, A comma B. And then we write our vector as A comma B, but we use kind of the pointed parentheses instead of our normal parentheses to signify that it's a vector. We say the numbers A and B are the horizontal components and the vertical components, respectively, for the vector. And then the angle between the x-axis and the vector, so this angle right here, theta, is what we call the positive direction angle. The position vector has that direction angle going up to it from the x-axis. So when we are looking at this picture should look pretty familiar because we've been looking at problems like this all semester when we've been looking at our SOHCAHTOA and putting our triangles and everything in our XY coordinate grid. So it's pretty much something we've been doing all semester. We're just applying it to some vectors now. So to find the magnitude of the vector, so remember the magnitude is like the length of the vector, we use this formula right here. The magnitude is equal to the square root of a squared plus b squared. That looks pretty familiar because it looks kind of like the Pythagorean theorem, also something we've been doing all semester long. And then to find our direction angle, we have the tangent of theta is equal to b over a. Should also look pretty familiar because it kind of goes with our SOHCAHTOA. If our theta is right here, this side over here would be the opposite side. This side would be our adjacent side. And so using our TOA from SOHCAHTOA, tangent is opposite over adjacent, so b over a. And then you just can't have a equal 0. Like it can't equal 0 because you can't have 0 in the bottom of your function. So example 1 says find the magnitude and the direction angle for vector u equals -3, 2. So if I'm trying to find my magnitude, I'm just going to plug it into that formula. So the square root of a squared plus b squared, so the square root of 3 squared plus -2 squared. So if I'm looking at that, 3 squared is 9, -2 squared is 4. So I'm going to have the square root of, well, 9 plus 4 is 13. Now, I don't know what the square root of 13 is. I can't really simplify it, so that's my answer. My magnitude is the square root of 13. To find my direction angle, I'm going to say the tangent of theta is equal to, and it's b over a, so -2 over 3. I need to work backwards and find what theta is, so I'm going to take my inverse tangent of -2 over 3. And then that's not really on my unit circle, so I'm going to use my calculator to help me figure that out. So let me pull my calculator up. When I'm looking at my calculator, I'm going to make sure I'm in degree mode for today's notes. And I'm going to, in degree mode, inverse tangent of -2 thirds, and I get that theta is equal to -33.69 degrees. We'll round to 2 decimal places for today. Now, normally our answers are between 0 and 360. So if I'm looking at this, it's not between 0 and 360. So for tangent, our period is 180 degrees. So I'm going to add 180 degrees to it. And you'll see that gets me to 146.31. The problem is that would be somewhere over here, and that's not really where I want to be. So I'm going to add 180 degrees again, which is going to get me 326.31, which does get me to my vector down in quadrant 4. So you may have to add the period once or twice to get to the proper quadrant for your angle. So I end up with theta, let's do a pen, not a highlighter, theta equaling 326.31 degrees. And sometimes you may have to go the other way around. Sometimes you may already have the magnitude and the direction angle, and you may need to go back and find the horizontal and vertical components. So to do that, we've got these nice little formulas here. A, our horizontal component, is equal to the magnitude times cosine of the direction angle, and B, our vertical component, is equal to the magnitude times sine of the direction angle. Then we would write our answer as an ordered pair. So that's kind of what it's got down here. So example 2 says vector W has magnitude of 25.0 and a direction angle of 41.7. Find the horizontal and vertical components. So to find my horizontal component, my A, I'm going to do that 25 times the cosine of my 41.7 degrees. So I'm going to plug that into my calculator, 25 times the cosine of 41.7 degrees, and I get 18.67. Then for B, the vertical component, I'm going to do 25 times the sine of 41.7 degrees. So 25 times the sine of 41.7 degrees gets me 16.63. So I'm going to plug that into my ordered pair, 18.67 comma 16.63, and there's my answer. So we're going to do the same thing for example 3, but now we have 3 of them that we're going to find. So if we're looking at this picture, we got to make sure we are deciphering which angle matches with which vector. And so that's where you've got to use some common sense here. If I'm looking at angle 60 degrees, that is in quadrant 1, so that's going to match up with the vector in quadrant 1. So vector u is going to be the one that matches up with 60 degrees because they're both in quadrant 1. Then when I come over here and I look at my vector v, that one is on my axis, so that's going to be the one that matches up with 180 degrees. And the vector w down here is the one that's in quadrant 4, so that's going to be the 280 degrees. Then you can also see that they all have little numbers next to them. So the 5 right here, the 2 right here, and the 6 right here, and those are their magnitudes. So we've got everything we need to go ahead and write each vector in our A comma B format. So for, let's start with U. I'm going to start with my horizontal component. So A is going to equal, well, I do my magnitude, so 5 times the cosine of my angle, so 60 degrees. So 5 times, well, the cosine of 60 degrees is on my unit circle, so I'm going to use that exact value from my unit circle. The cosine of 60 degrees is 1/2, so that's going to give me 5/2. So B, I'm going to have 5 times the sine of 60 degrees. So 5 times the sine of 60 degrees is square root of 3 over 2. So I get 5 root 3 over 2. So I can say for u, my ordered pair here would be 5/2 and then 5 root 3 over 2. If I want to look at v next, I'm going to start with A. It's going to be, this time 2 is my magnitude, times the cosine of 180 degrees. 180 degrees, also on my unit circle. The cosine of 180 degrees is -1. So 2 times -1 is -2. Then for B, I'm going to have 2 times the sine of 180 degrees. The sine of 180 degrees is 0, so 2 times 0 is 0. So I get -2, 0. Then let's look at W. If I'm looking at W, A is going to be, my magnitude this time is 6 times the cosine of 280 degrees. And this is where we're no longer on the unit circle, so I'm going to use my calculator. So 6 times the cosine of 280 degrees, that gets me 1.04. For B, I'm going to have 6 times the sine of 280 degrees. 6 times the sine of 280 degrees, and that gets me -5.91. So I'm going to have 1.04 and -5.91. And there are my vectors in my A comma B form. Make it a little bigger for you. Okay, the other thing we're going to look at today too, because we are doing the algebraic definition of vectors, is we are going to look at some vector operations, some vector algebra here. So you can add, subtract, multiply vectors. So we're going to look at that. The first part of our table right here is if I were to add two vectors. So if I have a comma b plus c comma d, I'm going to have a plus c comma b plus d. So I take the vertical components and add them together and the horizontal components and add them together. The next part is if I were to do k times vector a comma b, k is what we call a scalar, so that can be any number, just a regular number, not a vector, so like 7, 22, -4, could be a fraction, a whole number, anything like that. So if I have a scalar like that, I'm just going to multiply the horizontal and vertical components by the scalar. So the new vector would be ka, comma, kb. Now, before we talk about subtracting, we do need to look at the fact that if I have a vector, so let's say u is a sub 1, comma a sub 2, then negative u would be negative a sub 1 and negative a sub 2. So if you have vector u being the positives, then negative u would be where you just switch the sign of your horizontal and vertical component. So to subtract vectors, instead of adding them, you subtract them pretty much the same way. So a comma b minus c comma d, I'm going to have a comma b plus and then the negative version of c comma d. And so then it's the same as adding. You've got the horizontal components that you're going to add together and the vertical components you're going to add together. You're just adding the negative version of that c comma d vector. So let's kind of look at some examples that go with this. I'm gonna section off my space here. If I'm looking at the first one, I have u plus v, and it does tell me that u is -2, 1, and v is 4, 3. So if I'm looking for u plus v, this is where I'm going to add the corresponding parts together. So from u, for the first part, I would take -2, the horizontal part, and I would add it to the horizontal part from v, which is 4. Then to find my new vertical part, I would take the vertical part from u, which is 1, and I would add to it the vertical part from v, which is 3. So -2 plus 4 gives me 2, and 1 plus 3 gives me 4. So that's my new vector, 2, 4. If I want to multiply by a scalar, so b is -2u, I'm going to take the parts of my vector and multiply each part by that scalar. So my scalar being -2, I'm going to multiply the horizontal part, so the -2 by -2, and I'm going to take the vertical part and multiply it by the -2, so -2 times 1. So -2 times -2 is a +4, and -2 times 1 is a -2. And there's my new vector, 4, comma, -2. And for c over here, we're going to kind of combine multiplying by a scalar and the subtracting here. So what I'm going to do for this 3u is I'm going to multiply the parts of my u vector by 3. So what that's going to look like, I'll do it in pink here, is I'm going to have 3 times -2 and 3 times 1. Then I'm going to change it to plus, and I'm going to multiply the v vector, both parts, by -2. So -2 times 4 and -2 times 3. So for 3u, that gets me -6, comma 3. And for the -2v, that's going to give me -8, comma -6. And then from here, I do the same thing I did last time. I'm going to now add the corresponding parts. So I'm going to take the horizontal parts from both of them, so the -6 plus the -8, and then I'm going to take the vertical parts. So the 3 plus the -6. And when I do that, that gets me -6 plus -8 is -14, and 3 plus -6 is -3. And there's my answer. There we go. Okay, now this is not the only way you can see vectors represented when we are talking about like adding, subtracting, multiplying, that kind of thing. You can also see them represented by using unit vectors. So a unit vector is any vector that has a magnitude of 1. So we have the I vector and the j vector. The I unit vector is the vector that goes over 1 unit, and the j vector is the vector that goes up 1 unit. So you can see them over here. We've got I, and we've got j going over and up. I going over, j going up. And so if I have a vector a comma b, I can express it in the form of ai plus bj using those unit vectors I and j. So we've got an example over here in our picture. If I have the vector 3, 4, there we go, I could rewrite it as 3i plus 4j. So it's saying that I went over 3i and up 4j. So that's another way you can see your vectors written. So in your assignment, you're going to kind of go back and forth between writing it as a comma b and writing it as the ai plus bj and using the different forms to add, subtract, multiply, that kind of thing. So you can convert it and use the same way that we just added and subtracted, for example, 4 up here. And then once you get your answer, you can convert it back to the ai plus bj, or you can just do it as AI plus BJ, and that kind of makes it so that it's more of an algebra expression when you're adding or multiplying or something like that. So either way, however you would like to do it, you're more than welcome to. So whatever works for you. The last thing we're going to look at in today's notes is the dot product. If I'm looking at the dot product of two vectors, so we've got vector u, which is a b, and vector v, which is c, d, we would say u dot v, and it's given using our formula u dot v is equal to ac plus bd. So we take the horizontal components and multiply them together, plus the vertical components multiplied together. So we've got some properties of the dot product here. These are some properties that follow from basic multiplication and addition. They also apply to the dot product. So we've got like our associative property, our commutative property, our multiplicative 0 times u is 0. So we've got 0 dot u is 0, those kind of things. So the first one right here is u times v is equal to v times u. So u dot v is equal to v dot u, same idea. Right here and right here is our distributive property. U dot v plus w is equal to u dot v plus u dot w. And if it was behind the parentheses, u plus v dot w is equal to u dot w plus u, or v dot w. And like I just said, 0 dot u is equal to 0. And k u dot v is equal to k times u dot v. And u dot u is equal to u squared. So same kind of idea as all of our multiplication and addition properties. Same thing for the dot product here. And then if you want to find the angle between any two vectors, you can use this formula right here. So theta would be the angle between any two non-zero vectors, u and v. You can say that the cosine of theta is equal to u dot v divided by the magnitude of u times the magnitude of v. So once you know the dot product, you can then use this formula to help you find the angle between two vectors. So we're going to do two examples with the dot product so we can make sure we know how to do that before we actually get into this angle formula to find the angle between the two. So example 5 says find each dot product and state whether they are orthogonal or not. We would say that two vectors are orthogonal if the dot product between them is 0. So find the dot product. If it's 0, they're orthogonal. If it's not 0, then they're not orthogonal. So I'm going to start with A over here. This would be my A and B, C and D, like this is U, and this is V. Oop, I'm going to give myself enough room here. Scoot that over a little bit. V. So if I'm using my dot product, I would do A times C, so 2 times 4, plus B times D, so 3 times negative 1. 2 times 4 is 8, 3 times negative 1 is -3. So 8 minus 3 is 5. So my dot product is just a numerical answer. It's no longer a vector. Since it's 5, this means that these are not orthogonal. Then for B over here, same idea. I've got A, B, C, D. So 6 times -2 plus 4 times 3. So 6 times -2 is -12, plus 4 times 3 is 12. -12 plus 12 is 0, which means that these two are orthogonal. Okay, and now that we're kind of familiar with the dot product, let's find the angle between two vectors using that dot product in our lovely formula right here. So I'm going to say that the cosine of theta equals, and then I'm going to put the dot product on the top. So 3 times 2 plus 4 times 1 for A right here. And then I got to find the magnitude of each of them. Now remember, the magnitude is this formula that was on the first page of our notes, the square root of a squared plus b squared. So I'm going to have two square roots in my denominator here. So my first one is going to be the square root of 3 squared plus 4 squared times the square root of 2 squared plus 1 squared. So the cosine of theta is equal to, well, 3 times 2 is 6, plus 4 times 1 is 4, over the square root of 9 plus 16 times the square root of 4 plus 1. Okay, still simplifying. 6 plus 4 is 10. Square root of, well, 9 plus 16 is 25, and 4 plus 1 is 5. Well, the square root of 25 is 5, so 10 over 5, square root of 5. I can simplify 10 over 5, so I'm going to get the cosine of theta is equal to 2 over the square root of 5. And then I'm going to realize that that square root of 5 means it's probably not on the unit circle because there's no square root of 5 anywhere on the unit circle. So I'm going to pull up my calculator to help me here. Split view. So if I'm looking at this, I'm going to say that theta is equal to the inverse cosine of that 2 over the square root of 5. So inverse cosine of 2 divided by the square root of 5 gets me 26.57 degrees. Okay, if I'm looking at this, let's kind of draw a picture to show what this represents. So my u vector was over 3 and up 4. So let's do that one in pink. So it's, let's say right there-ish. My v vector was over 2 and up 1. So let's say about there-ish. So what we just found was the angle between them. So that angle right there was about 26.57 degrees. So we found this angle right here in between the two. And let's look at B, and then we'll be done with our notes. So cosine theta equals, well, the dot product on top would be 2 times 6 plus -6 times 2. And then my first square root is 2 squared plus -6 squared times my second square root for the denominator is 6 squared plus 2 squared. Now, when I'm looking at this, I'm just going to kind of look at the top first because I'm kind of noticing something here. 2 times 6 is 12. -6 times 2 is going to give me a -12, which means for my numerator, I'm just going to get 0. So it doesn't really matter what's happening here in the bottom, even though I've got stuff going on the bottom. I've got those two square roots. If I have a 0 in the numerator, well, 0 divided by anything just is going to give me 0. So I have the cosine of theta equals 0. So I can say theta is equal to the inverse cosine of 0. That is a unit circle value, which means that theta is equal to 90 degrees. Okay, so that's another nice characteristic. Remember we said if they had a dot product of 0, that means that they are orthogonal. So the dot product of 0, and that also means orthogonal vectors have an angle of 90 degrees between them. So if I were to draw a picture, the first one was over 2 and down 6. So let's say over 2, down 6 right here. The second one is over 6 and up 2. So right here, you can kind of see they've got that 90-degree angle there. So there we go. There are our notes, our last set of notes for this class. So let me know if you have any questions. Make sure you get started on your assignment that goes with this, and y'all have a good day.